we can get started. Andres, do you want me to introduce you or do you want to introduce yourself like tradition?
Yeah, so hi, I'm Andreas. I'm also here, one of the co-founders of the CUDA Mode Discord server. I'm a software developer currently working as an AI engineer at the German startup Aleph Alpha. Also working on large language models and inference. And yeah, I have some history also with Torch and deep learning in general and open source work. Always a pleasure to be in this position here and also to see our like universe of CUDA mode strive and prosper. Yeah. So yeah, today I'm really excited to present about ring attention, which yeah caught my attention some like weeks or months ago, and is I think like a really hot topic right now since we are getting into longer context models. So I call this presentation here ring attention, sequence parallel attention across devices that you'll see. Today we'll deal with a topic which is more on a higher level. That means across devices distributed. So we have an NVIDIA Nickel would be involved more than and of course like also the individual GPUs are utilized, but this is like now how we can orchestrate a larger amount of different GPUs. So yeah, quick overview. What we want to cover, or what I want to cover today is first like motivation, what's long context, transformers and the applications. Then do a little bit of recap for vanilla attention, online softmax and the logsum exp trick, so to say, which is the basis for flash attention and also ring attention, and then dive a little bit into striped attention. We'll see what this is, and flash decoding. These things are very closely related to ring attention. So if we start with yeah, long context LLMs, probably everyone has by now seen things like Gemini, which like officially will have this 1 million token context size, and in research they say they have up to 10 million tokens, which is now something which allows like completely different things to what we have had before. We can process multimodal inputs of videos and audios, and we can like extreme large text documents and also source code, of course. In this overview chart, we see a little bit is like from the Google blog post-release of Gemini. We see a little bit, I added some of the other open source models which we have currently. We have here especially the large world model stuff, which is from the authors also of the ring attention paper released, which is also in this 1 million range. We have Yarn Mistral, which is in the 128K range, so in the same as GPT-4 Turbo, and DBRX in the 32K, and Grok from XAI from yeah, in this 8K range, and in the middle here somewhere is like MPT, with this like alibi, linear bias attention is a little bit different than like for the position encoding than the others do probably, but here also in this middle of 65K. So we see there are some models available, and it's yeah, especially it's like dramatically increasing in size if we remember from where we were coming. And this long context models, they now allow a lot of new really cool stuff to do. So this is an example here from this large word models LWM model, where we see here is like I think this is some form of YouTube video which contains many other like YouTube videos, and it's 1 hour, and there's like a question, like a video question answering setup here, where the user asks for this 1 hour video how many lemons were in the person's car, and we see like it's like all the other models, they fail to it. And in this case, at least LWM can answer it correctly with there are 3 lemons in the person's car. And we see here at this frame, I guess this is referring to this frame, and it's working. In the paper, they like admit that it's like a little bit cherry picked, and in some situations it doesn't work as well as in this example. But yeah, overall, I think this like is very promising direction, and we really have to see what comes out of it when it's commercialized. So in general, we know we can now process like books, long documents, web content, chat histories, code bases, like really complete GitHub repositories, high resolution images. And then we go into this more interesting category like audio recordings and videos. And especially videos together with text descriptions, they some so a little bit complementary. If you think about like modeling the world around us, like not everything can be perfectly captured by text descriptions. So sometimes it's just like especially causal events and how things like very everyday things which are most of the time not described, like that things just fall down, that there is gravity and stuff. From a video, you immediately see how our world acts, and yeah, these models just become, with long context, better in predicting the future, and thereby also modeling our world, and hopefully it's like they become better general as like simulators of our world, which we can ask questions and also plan into the future. So a little bit in the background.
So Andreas, just a quick question. Are you familiar, like for Claude and for Gemini and for GPT-4, presumably like none of them have published any details regarding how they actually support long context lengths. Is your sort of like, if you were to speculate, and sorry, I know speculation is not always very useful. Would you speculate that it's like something closer to ring attention, or like do you have like some sense of like what they might be using?
Yeah, so that's a very good question, and I also think that should be said here, like as a disclaimer in overall this presentation. I don't know exactly what these commercial implementations use, and in some way, I also doubt that it's ring attention, at least for this very high, like 10 million and so on contact lengths, because just the inference is so expensive if it's like really done in this way as it's done for ring attention. So I'm not really sure about this. It could be, and it's like the closest we currently like is published in research, and they show that it's also feasible to do this into some extent. But it's like I don't know what the cost will be for this like 10 million if it's like really released as a commercial product, but it will be substantial. Yeah, maybe we can later also talk a little bit about the cost about training, which in the LWM paper there were some interesting comments that for example, takes like 7 minutes for one gradient step with like in a 1 million token training setup. So that you can also basically have like 200 steps per day, and it's of course like ridiculously. And you have to then first train on smaller models, smaller context size, and then you can scale up and only do a little bit of steps. But we'll come to this maybe. Maybe first, if you look at this. The background of this multimodal things work, and that everything can be processed by transformers. So maybe like all know this like little diagram here. We have like things go into the transformer. We have like this multi-headed attention, and then a feed-forward network, and this like n layers wide. And the question is now, okay, how can we get everything in these token and embeddings, which I can process so well by transformers? There are different ways, of course, like vision transformers, you may know, or we have where basically the direct linear projections of the input images into the token dimension. And here's like more general, the Lava case would say that we have like vision encoder. We take some, for example, an image, and we somehow convert it into like some like tokens for this image, and then we have other language queries here where we embed the language tokens, and basically can make a question and generate autoregressively then the answer here. And the similar thing can also be done for like of course videos, not only single images. If we have like really long context, you can use, for example, VQGAN as an encoder. So this takes in this LWM model, it takes 256 times 256 input images and converts them into 144 tokens each. And then you can basically stuff in a lot of these images, generate them from a video, and also do text token prediction, and basically either complete to describe and caption this image, or to ask a question, depending on what was also trained in the model. But they all have in common that they have this autoregressive transformer here, and this is like the same basically setup and like overall broad architecture that we have for Lava, or that we have for Llama in general, or for this LWM. The only thing that we need is, of course, if we want to input a complete video here, we need an extreme large context size so that we can really process a lot, or like put input a lot of different frames, and then make our question about this. But this really allows us to do text, image, video as individual inputs, or video to text, text to video, image text, and text image. So we have all different combinations. We can also generate with the things. For example, in their paper, they have classifier-free guidance as a technique where they can steer basically the autoregressive generation and thereby also produce images as output, not only text. So this is as an overview. The challenge that we have if we want to go this really long context is we run out of memory quickly, at least at some point. So here directly quote from the ring attention paper is with a batch size of 1, processing a 100 million tokens requires over 1,000 gigabytes of memory for a modest model with a hidden size of 1024. And yeah, this is like obviously still a little small model, and we have to realize that for attention to work, we have to materialize the input of the attention. We can, like on the fly, compute the inner things, the score matrix. We can online compute the softmax, as we'll see, but we need to somehow store the inputs and the outputs, and also the log sum x and the different, like the gradients for the output, of course, for the backward pass. And if you look at current really high-end GPUs, we have this NVIDIA H200, which has 141 gigabytes high bandwidth memory, and with the AMD MI300X with 192 gigabytes, it's a little bit more. It's a very good device, of course, for inference. And in the then upcoming here announced a couple of days ago, the NVIDIA GB2 of can we use maybe multiple devices to process these things. And there are like different approaches to. Some years ago, there were linformer and there's linear attention, and there are different sparse and windowed attention techniques and so on. Like this would the A. Then we have B, rec, and vector DBs with approximate nearest neighbor search and something like locally sensitive hashing. So these are also, of course, possibilities to do, or what we'll discuss today with ring attention is just like brute force compute. So we don't do anything about the quadratic scaling. We just compute what's necessary and do all the operations. We luckily can a little bit do something about the memory, so that we don't have quadratic scaling in memory. But yeah, it's still like the brute force method of really computing all attention scores. Yes. So if we look at vanilla attention as the basis, maybe all of you know, or most of you know, we basically have like two matrix multiplications involved. There's like this query times the transposed keys, which gives us the attention scores, and they are passed through a softmax function. And what we get then as like individual rows in this attention metrics, basically that comes out. One is the probabilities that each of the values should be used, and then we can basically multiply this with the values to predict then one output per query. So this is also important. Like even in vanilla attention, we have this opportunity to split the computation so that we could theoretically compute each outputs. That means for each query input individually, they don't like these tokens don't somehow depend on other things. So every query can be processed in theory individually. Normally it's done in a whole batch, of course, for like efficiency reasons. But if you want to like minimize memory usage, also here in vanilla attention, you could do this split at the queries. Problem is here we have this quadratic attention, which is like sequence length times sequence length in size, and probably all, yeah, maybe you already have this concept. This is like the big problem. We have this quadratic scaling. This will kill us at some point, and therefore we need to do something about this. And here I want to show something that I found in the ring attention paper in the appendix, which was a little bit surprising to me, I would say. And that's actually the ratio of flops that are necessary to train a given data set with different context lengths. So we see here in this context length axis, we have basically it says as a base it takes a 4K context size, as this would be 1.0 as a ratio. And then here we see the scalings like 2x, 4x, 8x, and so on. And here also the resulting context length that we have in the then as the context length, so from 8K to 128K, and here to 100 million context lengths. And on the other axis here, we see the model size. And here in all these fields, we see now what's basically the ratio is. And if this formula, which they present, which should be representative for the attention mechanism, I guess with the feed-forward layer is 24 sequence lengths times hidden size squared plus 4 times sequence length squared times hidden size. If this is like really a valid formula which they present, then you really get these values. I was very surprised. I did the computation myself in Excel, and I can confirm that these values are correct. So that means if you take something like 65B, and like a largest llama, which we currently have, and just would train it instead of its default context length with, for example, 256K context lengths, we would only need, quotes unquote, only 5.8 times the compute that was necessary to generate the original model. And this is like quite surprising because the context length is already 65 times larger than it was in the beginning. And some part of the answer is, of course, that you need in total like less batches, because each batch now would process 256K, like each sequence, instead of 4K, for example. But you can also make the math and also maybe upload my Excel sheet, which I did for this, if you want to do it yourself. Like surprising is that for larger models here, we have like GPT 3.5, maybe 175 B parameters. It's already getting smaller. At some point, of course, this quadratic scaling kills you. So if we get in the really long things here, we will just be killed by the quadratic scaling. But it was for me surprising because it is like really long, it's like feasible much longer than I thought initially. Okay, so then if we go into a little bit into the details about what we want to do with ring attention, also do it with flash attention, is the softmax function here. You see the softmax function basically does this explanation like e to the power of x for each element and divides here by the sum of all these things. And the challenge is that this computation, basically to produce an output value for a given xi here as input, we need to know the full denominator, the full sum over all these things. The full sum over the row in this score matrix, which we get here. And this is like a little bit of a problem because we want to compute this blockwise. And in flash attention and ring attention, we need to do this blockwise, and we'll now see, we'll now look a little bit into how this is done. But this like has to deal with basically parts of this sum in the denominator. And I want to go to this like step by step, also a little bit with Torch. I have also a Python notebook, which you can maybe check online. I'll link to this later. So maybe we start a little bit by a very naive softmax function. So just to convert this formula here into Python, we see that we have like this x element-wise x call here on this, and then divided by actually the same and its sum. So this gives us the softmax. We can confirm this. We like generate 10 random numbers, call the normal softmax function from Torch, the native one, and then our naive one, and basically test if all close. And we see basically from the output it's like identical from the computation. So we are good, at least at this range of parameters. Slight problem with our naive function is it's very unstable. So if we, for example, scale the input here, this random, like normally distributed random numbers by 100, we already end up with something which is like obviously like not desirable. What we want, we have like this none value, and we maybe see later. Yeah, we see later how this can be fixed. But let's first look into the blockwise computation. Just as the warning that the naive one can't be used directly. So our goal is basically to break the softmax into chunks here, and we can just look what we want to do. We have this random number, and we would like x, and we now split it into two equally sized chunks, x1 and x2. And for each of these chunks, we compute the naive softmax function. So we can print what we get from this one. And what we actually want later is to somehow combine these again into the target. So that means the softmax of the full x for the full 10 values. Well, we have only, like for our blocks, we only see in the individual blocks these 5 logits for which we then compute the softmax. So it's like easy to do the splitting here. The question is now, okay, how can I get my target back again? And like a simple trick to do this is a little bit to undo what we did in the naive softmax or in our softmax in general. We can see that this is here divided by this xexp.sum. So this is like our sumexp component. And in order to just basically compute what the naive softmax function would have computed for the full tensor is, we can basically now like multiply again back with this value, which we see here basically. This is like sum x, SE stands for sum exp here. And yeah, if we have access to the values in this case, which was like naively assume, then we could compute these values again. We could then scale basically it back so that we would undo this normalization here from the softmax and like correct it by the correct full sum x, which we would get from like combining both together. And if we do this for both here, like S1 corrected, S2 corrected, we can see if we concat this two tensors together, we arrive at the same value as the original like target here, which we had before, and we get an all-cause value of true, which of course is good. But in this case, we still need access to all the values, so it's like a little bit pointless. Just bear with me a little bit. You will see where this leads to. So we can now do this also in a more numerically stable way. So here again, we make like a setup with an x, we like 20 random, normally distributed random numbers. We compute our like a value, which is like our test target, which we want also to get with our function. And we split this here again here in two chunks to simulate our blocks that we have. And now we define a little bit different softmax function, so it's no longer naive. In this case, we do a stable softmax. The great thing about softmax is that it's scale invariant. That means or shift invariant. Sorry. That means we can add or subtract any value from the individual things unless it's like the same constant that we would add or subtract, which you can basically see from if you look at the softmax function. It's this addition ends up basically as a factor which is in the numerator and in the denominator, so it basically cancels out, and that's basically the fact that we can use to shift our input into like a more easily processable range, in thereby, for example, by taking here the maximum of the inputs and subtracting the maximum then from all values. That means basically all values are smaller than 0 in this case here, and that means they are all smaller than 1 for like after the e to the power of x for this element. And this is like much easier and better for us to handle, and we can then also, if we would now pass our input that we had, where we got this none into this new function, we would get a reasonable output and also the same output as the official PyTorch function. And another thing that we also can do is we can directly return this thing which we on the other slide basically computed externally again. We can also directly return here this sum x, and in the case for us to have like a little bit more stable thing and to like a little bit nicer in the value range, we can return it in a not exponented, like in this not e to the power of way, but in a logarithmic log space, and get this value. Basically here we need to correct for the maximum, which we have like subtracted. But basically, this gives us the same option that we can, like if we would take this exponentiate it again, we could then get basically the original denominator that that would be produced by summing up all the exponentiated values from the x element inputs. And here we can now do the same combination of things which we saw on the previous slide in a like a little bit more stable way. You can see here that here is basically the like naive way to do it, written in C1 equals B1 times like we undo the normalization. Then we have here the basically the total. Oops, sorry. The total normalization denominator and divide by this, and thereby we get the correct value for the first slice, and can do also this for the second slice. But the thing is, we can take this formula here, which is like basically would be like A divided by A plus B. So A is here and A plus B, and we can like write this a little bit different into 1 divided by in brackets 1 plus B divided by A. And this basically can be done then completely in log space, so that we don't have to really materialize this exponentiation here, but we can do this by subtraction. And this, of course, like much nicer from the value ranges and much more stable. But it computes us basically the same outputs, and thereby we can get here if we do the same thing with A and B. So A was our original. Oops, our original. Sorry. Where do I get back? So A was our original softmax output, and B is now what we computed here with this formula. And if you do the comparison with all close, we get true. So this is really nice. And the question now, okay, what does this like, why do I tell you? As the thing is that this like direct formulas that you see here also appear in the ring attention code directly, which we'll talk a little bit later about ring attention. So this is like a peek into the future. You see we have this update out at LSE log sum x function here in the original ring attention code, and here in these two lines, they basically are the same which we saw on the previous slide, where we now can combine two different blocks together with help of this log sum exp and produce an updated out value. The thing is that this cannot, what we saw before for directly on the probabilities, so the outputs of the softmax function can also be done for value projections and also for accumulated value projections, which are effectively linear. And this is like the trick which is used by flash attention. It's also used by ring attention to allow that we can split things into individual blocks and compute them, then accumulate basically the different things, and always correcting for the factor that the new block gave us for the increase in the denominator, so that we can then scale it, what we have so far, a little bit, add our new output to it, and we get the correct value in the end. So this is really magic here. If we, I found this nice animation, which is, I think, I'm not sure if it was designed for this, but it's actually exactly showing what we need to see. So here, for example, you can see, let me first stop this and talk a little bit about the graphics. So you see this, and at the left you see basically the queries which go in, and in the horizontal axis we have the keys here. We have here the outputs which are produced by our softmax function, and here the values which goes like for every key we have one value, and for basically every query input we produce one output. If this is like complete self-attention, everything will be the same. So we have the same number of queries as keys as values, but keys and values are always the same, and queries could be like for cross-attention, for example, something different. But we have here, we can now take like a smaller batch, like split this into a little number of queries, and then process it first with a section of the keys, which we see, for example, here. Then compute our softmax only for this individual block, and for this have like an intermediate output here in the output. Then the next, I take basically the next block here, and like compute again my softmax here, compute again the projection with the values, and I need now to somehow combine what I had before in the outputs with like the new output from my block here. And this is exactly done what we have seen in the way that we have seen before, where I take the existing thing, I need this additional logsum exp information for this to work in order to scale this back to like basically see the difference in that it would have has to have, scale this a little bit, and can then add and accumulate over time, so that I really can do the softmax computation and the value projection in an online, in an iterative way, where I don't need the full materialized score matrix or the full materialized softmax, and also not basically all the values at once. I can compute them in a blockwise fashion and then always update. In the end, I will get the exact same result as I would have in the naive way, where I had like fully materialized this matrix. So this is like the basics of the basis of. Let me next. So this directly we can see this update out in LSE function, which I showed in 2 slides before, is directly called in the ring attention code in the next open source implementation of ring attention, which is really nice and I can recommend. And this, the great thing about this is that ring attention you can think of as a hierarchical, like highest version of flash attention, which runs on the device level, while on the individual devices there actually runs then flash attention as with the same similar algorithm, just like splitting blocks inside this device and not over the devices, which ring attention does, as we'll see in a couple of minutes. So here you see basically, look, we have flash attention forward. This is unfortunately not the direct API function from flash attention. It's from the TreeDAO repository, but it's an internal function, because normally this logsumx is not directly returned, but we can directly use this function and then get this block logsumx value and the block output, and then integrate it, basically combine it with the existing output that we have with this update. We also see here some communication already. We'll come to this in a minute. Just you see that like this is the actual implementation of how the ring attention algorithm works. Can recommend like Susie Lin flash attention repository if you want. So now we have like really looked into the inner details of this ring attention. So let's look what's actually ring attention. So therefore I would first like to talk a little bit about sequence parallelism. So there are different, as you may know for distributed training, there are different parallelism forms. So for example, we have data parallelism, where we just take like different batches for a data set and have the model directly sharded on all our devices. And then we have other things like for example, tensor parallelism or pipeline parallelism. Maybe like pipeline parallelism is pretty simple to understand. You have like a large model with like, let's say 90 layers or so, and then you would say I take like 3 devices to process this model, and like 30 layers are on the first device, 30 layers on the second, and so on. And we have a new thing which basically is coming now, sequence parallelism. And in sequence parallelism, we take the sequence here. In this case, for example, the microbatch, you see like this is sequence parallel, and the first 2 tokens of the sequence we would compute by this process on the first device, and the last 2 tokens we would process on the second device. So basically we split. We have the same model on both devices, but we split the batch in sequence-wise. So in the sequence dimension, so that they are like the same sequence is sequence is split and processed on both devices. So, and how to this like it's supposed to be a naive thing without attention, and now we need to also look into how this can be done with attention. So for each of our inputs here, for the xi's, that would be our tokens, they would be embedded, and from these embeddings they would then be projected into like query, key, and value each. And I would then have like for a sequence a certain number, like the first n, for example, on the first device, the last, and then on the next device, depending on how many devices I have, I would split this across devices basically. And yeah, the thing and the main concept of ring attention is then that we can also do this blockwise computation on the devices. This is the same as flash attention does it, like by splitting across the queries and computing then for queries, like every basically like taking a certain block of the keys and computing the intermediate output, and then taking the next block of the keys and so on. This can also be done on the level of multiple devices. So we have here, for example, this little diagram here, set up with 4 GPUs, and we would now split things so that we in the beginning have really like the queries and the keys and values belonging to the first of this first quarter, basically, of the sequences on the first GPU, the second quarter here on the second GPU, third, and so on the third and fourth. And the thing is, of course, in order to compute an output for each query, I need to see all the keys and values. At least for, let's assume like not causally masked, like full attention in the beginning. This is simpler, so we would assume that we need all keys and values to see all keys and values. And this, is basically done for ring attention in the way that these keys and like queries stay on the individual devices, and the keys and values, they are sent around in a ring fashion, so to say. These GPUs form a ring, and these keys and values, so for example, key value pair like 1 is sent to GPU 2 while it's like computing its first update, and it's receiving like key value pair 4 from the fourth GPU. So it needs always to communicate with the next and previous member in the ring. And the thing to know here, or to why this works or can be done, is that the order in which we do these key value chunks is not important for the output. So I can take any order unless the only thing I need is basically to have seen all key values in the end. And of course I need to like know which things belong together. But as long as I do this, I can directly compute the correct output. So we basically see here the order computations can be arbitrary. This is leveraged by ring attention. We split the queries, keys, and values across n hosts, which you see here, and then they form a conceptual ring. And one pass completes when every node has seen all parts of the keys and values. And the trick now is that we can send and receive while we compute. And if the computation is long enough or takes long enough, like the sequence is long enough, so to say, then this is like causing really zero overhead in general, because the transfer of the data takes less time than the computation. I think in the paper they have an analysis for this, and depends a little bit on the transfer speed that you have. But approximately like I think like 6,000 or so something. It should be amortized, and maybe you look at the numbers in the paper, but at some sequence level, it's basically zero overhead, which the communication takes. So it's really nice. We can split across the GPUs, extend the memories thereby by a factor of number of GPUs, and the transfer is for free if you want, or like in time. It doesn't require more time. So what we saw before already in the like real SUSY-LING implementation is also as an algorithm in the paper, of course, in pseudocode. We can also glance a little bit over that. So in general, we have this input sequence X, and we have the number of hosts which we start with. We split the input sequence into n blocks, so that each host has one input block. We compute the query key and values, and basically have then these for each input. We have query key and values. So for each host has then this of the chunk which itself had at the beginning. And then we go over all transformer layers, which we can ignore. But then the important part is here that we have like we go over n-1 steps where we transfer and compute. For each host, we have like concurrently, we do basically our attention, which is like, for example, flash attention, as it's in the SUSY-LING flash attention thing, using the local query key and value blocks. And at the same time, we send the values and keys to the next, and we receive also keys and values from the previous host. This is in this ringwise fashion, done until I've like seen all. So this is like n minus 1 because I of course have in the beginning already like my local like parts on my machine, and then in the end I can like compute my directly output, so that every node basically computes the output for the queries which it had, and then we can later of course could then combine this again. Yeah, then I want a little bit for as a preparation of a striped attention, look as the causal masking. So this is like, of course, maybe the simpler aspect here, but in transformers, if you have the score matrix computed, so for every dot product between the queries and the keys, you want to ensure for that in order to autoregressive decoding to be possible, that no token attends to something which is like in the future or like in a higher sequence position than it itself has. Because during decoding we don't have these tokens yet, and so it must only depend on what has been already produced in the past. And this can be done by having our attention, taking the attention mask and ensuring that all these values, which are here also above the diagonal, that they are zeroed out here in this mask, which means before the softmax they would get a minus infinity. So normally you see in the softmax, in the dot product attention code that there's like a masked fill where all these values, which should be masked, are then replaced by minus infinity before the softmax is computed. In like efficient kernels, like flash attention, for example, we don't need to materialize this matrix. If we just want the standard causal masking, we just compute them on the fly, which is like easy, just as by this formula. I see that if this I index is like smaller or equal than j, we can take this dot product. Otherwise, we just don't compute it and set it to minus infinity. And for the whole blocks which we compute, like if this would be a block here, we just could completely skip it. So this is, for example, also done by efficient implementation like flash attention, so that in reality it's like almost half only of the computations that we need to do because the others are masked out. Problem now for ring attention is that this leads, unfortunately, if like naively applied, to the situation that some nodes will be completely idle. And the problem with ring attention is that the slowest node in the ring determines the pace in which we can compute. So if some things like are directly completed because they are idle or they don't have anything to do, they are super fast, while others have a lot of compute to do. And it can't go to the next step until the last or slowest thing has really completed its computation. And this is, as you can see here, all these black things, they are basically idle, while some others are active. And in this like third round, we only have like the last like GPU is active and the others would be idle. And this is of course like undesirable. It of course takes also longer than it should be, because we don't evenly distribute the work. We have now evenly distributed the queries and keys and so on, but the work is not effectively distributed. So if we can maybe look this a little bit clearer in this this diagram, which I made this ABCD to show where things come from. So you see this different causal masking elements here with the different characters, and here from this total causal mask which exists, to just understand where these things come from. We see basically this different vertical lines here, which they are then materialized by this. So in the beginning, we have, for example, this the main diagonal, and then we have these others. And this, is basically a problem with the stripe attention addresses. Maybe just to a little bit go over this here, we see always the case which we had before. If the so I wrote right here, if the I, so the query is smaller than the key index, then we can use this value. Otherwise, it's like ignored. And exactly the same we can now see here. So for all these cases here, where always when the key value is like higher than the query value, we need to mask these out. So for example, here in this, we see like everything is masked out, in the next round, we get here from the first GPU gets the KV3 elements from the which were here in the first round, and these are like have indices 12, 13, 14, 15, while our queries are 0, 1, 2, 3, and this of course like the queries are smaller than these, and and therefore like they have to be they can't look into the future, and they have to be completely masked. While the others here now are nicely utilized, because in these cases, like all the queries are larger than the key indices here, and depending on this, what's happening, basically you get these masks, and then this problem with the idle nodes. And unfortunately, of course, causally masked models are very common, so we should do something about this. And the solution now that the authors of the striped attention paper came on is to reorder just the query keys and values. So if you have like the original thing where everything is like nicely ordered from increasing from 0 to 15, here they have now for striped attention this permutation operation, which basically takes care that the first GPU, for example, not gets like 1, 0, 1, 2, 3, but gets 0, 4, 8, 12, and so on. And the first GPU then 1, 5, 9, 13, and so on. So this is like a very simple permutation pattern, which also now leverages that we can compute things in this arbitrary order. It's like not an arbitrary order of these chunks, but we can individually like reorder these things. The only thing that we need to do in the end, because like for every query is like one thing computed. So for the outputs, for example, of the first device, we would now have for a sequence the zeros element, the fourth element, the 8 and the 12s, and to have like to restore the full output sequence, we would have to undo this permutation after the full computation. But the whole computation can be done in this permutation. And of course, we need also to divide the attention mask accordingly. Or like if we have this formula with the queries smaller than the key indices, it automatically is like materialized. So here we now see what happens if we do this. It's now a similar diagram as we had before. But now we see nicely, we now have never these completely idle nodes nowhere, and we have like nearly causally masked things, everything. Like these and these, they are not perfectly causally masked, but trick is if we just drop the first query and the last key, then these become like smaller matrices. Like you can imagine just to have this 3 by 3 instead of 4 by 4 matrix. And this is again then fully causally masked, and we can then even use the standard flash attention function for it by just dropping first query and last key. And this is like very nice. For example, is leveraged by the Susilin Stripe, like flash ring attention implementation, open source. And yeah, thereby we can evenly nicely distribute the work among the workers as well as the data and the computations. Yeah, so it's really nicely distributed. As the last thing today, I wanted to look a little bit into decoding and something called this flash decoding. The problem for long context is that flash attention itself is not really optimized for long context inference. And also, actually, the ring attention thing itself is not optimized for inference, at least not for token by token inference. But during token by token inference, we only have like one query or like a small amount of queries, and these are for the batch elements, and these are then have to be computed for all the individual like values and keys. And this is like different to what we had before with the ring attention, where we had the queries basically on the individual devices, and then the keys and values were sent around. Here, for inference, we need to do, but this would be like very inefficient to do with like a very, very few queries also. But what you of course could do is to send around the queries, or to send the queries to all devices. And this is basically what flash decoding the flash encoding is developed by TreeDAO, and also think something like Francisco Matha I'm not sure if he is still at Meta, but was at least at Meta before. And then we get one slide further. We see now what flash decoding does here. It does a similar thing as ring attention, but it doesn't send around the keys and values. It directly sends the queries to all devices, basically, then computes on these devices blockwise basically the output that block soft attention was block attention output, and uses an additional reduction step, but then does this combination across all the devices. So here we can then effectively also leverage the compute of all devices. So compute all the dot products between queries and keys on all the individual devices. Also do the value projections already for this different the fraction which we have, and then we only need as an additional thing the reduction step. I have not seen this really in production, or also I don't not have really experience with this, so that I'm not sure how much the reduction step is in comparison to the individual computations. I assume currently that it's very lightweight, and it's only taking a minuscule fraction of the thing, so that in total we can really split up the computations and speed them up. Ideally it would be up to n times if we have n devices. Yeah.
So Anders, so one interesting thing we can do here is it's actually quite easy to measure this stuff. There's so there's the PyTorch profiler should let us know, and then there's also this really nice profiler that comes from Facebook Research called what was it called again? HQA or something. I forget the name, but it'll sort of explicitly log your communication versus comms overlap. And so I'd be sort of really curious to just take cleaned up implementations of ring and flash decoding, measure the overlap, and then compare that to sort of a toy educational implementation, in the same way that you had for the online softbanks in the beginning. I think that would be very useful for people next time. It could be a natural the next lecture if you or anyone else in the audience is interested in picking that up.
Yeah, definitely a cool thing. So I have not found so far a really good implementation of flash decoding. So I have multiple blog posts about it. Also on the PyTorch blog was one, and the thing which I link. Where do I link it here? Somewhere I think I also linked to it.
It's probably in the Xformers code directly, I would imagine. But I don't know if the implementation there is a toy implementation. But yeah, that's where most of Francisco's work goes. And yeah, thankfully he's still at Facebook. Yeah. It's good for the stock. It's I'm happy he's there.
So just as the last thing, because that's also already what I wanted to present today is really this paper history. We have this 3DAO, of course, as a flat attention as the initial thing, and there was also other memory efficient attention papers. But then really this work, which led to also the world models million length video language with ring attention, was really with how Leo and others, which started in August 2023. We have started with the blockwise parallel transformer. Then the ring attention with blockwise transformers. Then there was from somebody else striped attention, and then again from how Liu word models on medium length video and language. And this is basically the state of the art currently, and also matching almost what Google does. Yeah, for you, I have this link to the ring flash attention, which I really can recommend. We have also in our channel the ring in our Kudamo Discord the ring attention channel, where we discuss it, and we also want to train our own models. I'm still working on stripe attention implementation. I almost finished, just some of the tests don't still have some minor errors, which I need to check if this is a numerical error. It probably is some other bug which I need to fix my tomorrow. But if you want to help, if you are seriously about training and want to learn about ring attention and training larger models, feel free to join the ring attention channel and ping me or somebody else there. I have also this log, how to log some exp again as the IPython notebook. If you want to go over it, it's maybe was a little bit fast today. And yeah, this is a way to really look into this, and also play around a little bit with this, and maybe you can also extend it if you want, and send a pull request. Yeah, so this was my talk today about ring attention and and the surrounding friends of ring attention. If you have questions, now would be the right time to ask, and maybe I also can look into the chat because I didn't paid attention to the question.
Thank you so much, Andreas. Like everyone, please give like a huge round of applause to Andreas for this awesome talk. I think you covered like so much ground. Like I feel like I really want to go like deeper and like with between all these papers and code repos. Like I'm quite excited about like diving deeper after this. So thank you, Andreas. Really, it was an excellent talk.
Yeah, cool. Thanks. It
And
was a pleasure.
an audience seems to agree. Perfect. So,
yeah, the cool thing is really that we have this world models now, and or like that we go into the direction of world models. I would say that these things allow us video processing. And asking questions was unthinkable for me a couple of months ago even.
So we already have our first question, which is how does flash decoding compare to speculative decoding?
Yeah. Okay. So speculative decoding is something where you have two different models. You have a drafting model, which is a smaller and faster model, which basically you use to decode to propose some decoding output, and then you verify this output of the like the drafting model with what the larger, slower model would have been computed. And the trick is that you can do this in a batch, so that it can take multiple tokens which have already been produced by the smaller, faster model, and this it's fast, of course, to produce multiple tokens and like probabilities for multiple tokens with the large model. And if you find that this the probabilities would fall into the ranges or cover the ranges which for the produced values of the drafting model, you just can accept them, and the drafting model can keep on. And only in the case where you say, no, this is like my larger model would have computed something completely different, let's discard the draft model and do the real thing with the big thing. So this is also like speculative decoding and flash decoding can probably just be used together. They are like orthogonal. So if you want, this is the one technology is like using two different models. The other is like decoding faster for a single model.
Yeah, like that's my understanding as well. It's like one is for longer sequence lengths, and the other is just to make your autoregressive decoding quicker. So they are orthogonal, I believe.
Yeah, so that's maybe also like something, because there's obviously some communication overhead. So flash decoding probably is not worth, like if you have only like 10 tokens, then up to a certain threshold, it's probably wise to have like on one machine the things. Also, which I'm not 100% sure about flash decoding is how they reorganize, when they do reorganize the keys and values. So if you do token by token generation, of course, you start with a certain, like a prompt maybe, which you have processed, and then you add tokens and tokens. And it's like for flash decoding to be optimal, the keys and values need to be split across the devices. So there needs also to be some like schedule and where the current keys and values that are produced will end up. So I have to look deeper into this, how this is actually done.
So there's a lot of questions, by the way, left if I scroll up. Like another one from Elkun is, do you need shared memory for sequence parallelism?
So this is independent. Yeah, so shared memory is used inside like the flash attention, of course, like the main thing which leverages. But for sequence parallelism is on a much higher level, so to say, where we say, okay, I have like some tokens go to the first device of my current sequence, some tokens go to the second device, and so on, the other devices. And so I split the sequence wise across devices. And this is like on a device GPU distributed processing layer. It's basically independent of the individual computes, which also, of course, then make use of shared memory. So it's always good to have memory, and it would be better to have more shared memory, of course. So it's strictly speaking, for sequence parallelism, shared memory is not like relevant or doesn't have to be used.
All right, so there's a lot of questions left. So another one is like, I think there was another one like with rumors around like what is Gemini doing. I think it seems like we don't know, but like I don't know if you want to speculate, Andreas, or if we want to just go to the next question. I'll leave it up to you.
Yeah, I personally, I'm really not sure. I have no direct connections to, so and I have no insight. So I doubt it a little bit, as I said, because there's like so extreme, like the quadratic scaling at some point just is becoming a problem, and 10 million tokens already is a lot, and there's like it biting you.
All right. Another question. I think this relates to your point around like basically comms bottlenecks, which is
Mhm.
how feasible is it to use like something like Ring Attention with consumer cards if they're connected through
Yeah.
PCIe?
So I think this is absolutely feasible. Um, yeah, we currently have, for example, in our ring attention channel, we use a setup with two A5000, I think, so it could also be 390s. So this, if you consider this still as consumer, I would consider them as consumer GPUs, and they could also be, of course, connected by NVLink, then even better. So I guess like you can definitely, normally you don't have like more than 8 probably in a consumer setup, but for like maybe dual GPU setups definitely can be used. And you can also like double the sequence, like you can double the memory. It's just a way for a single sequence to compute with with all the memory that you have on different GPUs. And whether it's like 4090s or like what people are currently building, or maybe like the tiny grad machine, but it's like tiny corpse computer in the future, which maybe also an AMD CPU, GPU. Sorry.
Yeah, so S3 Dots is making, I think, reminding us that like consumer GPUs don't support P2P over PCIe. I know this is true for 4090s. I'm not sure about like if this is like generically true, because I would need to buy more GPUs to check for sure. Um, I think another question is like from Lewis Ulmer, which is how is ring attention
Yeah.
used in inference? Is it straightforward for a single few GPUs inference setups, or is it mostly like a training technique?
It's, in my opinion, mostly a training technique. The thing is, and I don't want to figure out what exactly they do. They describe in their word model paper, this large word models thing, that they have an optimized version for ring attention for inference. And they also describe at some point that they split somehow at the attention heads across the different GPUs, but I'm not perfectly sure how it's done. So this flash decoding is seems to be much more reasonable, because if you look at this, the normal setup is really you have these queries. They sit on the GPUs and then is sent around the keys and values. And this, in my opinion, in this form doesn't make sense for token by token generation, because you then only have like one query. And the question is like, what would you do then? The flash decoding makes sense. You send the same query to all the GPUs, and the keys and values stay there, and then you have a reduction step afterwards. So this is, I still have to figure out, like maybe look into the code from what they published, how the ring attention authors themselves use ring attention for inference.
Um,
So
so, so,
unfortunately, can't fully answer this. Yeah.
so you did also end up answering by accident like Jam's next question, which is like, why is
Oh,
batch byte size one LLM inference memory bound, and why does it end up being matrix vector multiplications instead of matrix multiplications? I can answer this.
yeah.
Like basically, just
Okay.
batch size one. It's because you're like your queue is a vector, so it's like it ends up being like a vector to matrix multiplication. It's memory bandwidth bound because like the compute cost of that is like very low, but you still need to send like the data over to the GPU. And so if you take a look at some of the lecture for like arithmetic intensity, you'll get like a very strong intuition for why this is the case. I think the next question, I actually really like this question, so it's by I3 dots. Okay, so there's a bunch of people here with I3 dots names. Like there's N3 dots, I3 dots. I think it's like we have the three dot
Yeah,
mafia here.
that's like stream mode active. You
Oh,
can
I see,
say
I see.
it's like to anonymize
Oh,
the
I see, I
people.
see. I see. So I3 dots is saying so flash decoding is like MapReduce but for QKV vectors.
Yes, yeah, basically they're already there. Yeah, they are not. But you map the, so to say, you duplicate actually the queries, because like the same query is sent to all the different devices, and then afterwards, of course, you have this reduction step. Yeah, so you can, it's some, you can say like the map reduce. Yeah, I guess this is fine to say for this.
All right. So then,
In general, maybe like for the inference, because this is always I see so many people who because I work in inference, and many like even researchers who worked in training, they are not fully aware of like this the difference between training and inference, and like how different this like it really is, because this goes to this vector matrix product. Because you have if you assume batch size 1, you really have in inference like only one of these like tiny queries you have, and you have all these keys and values which are in the key value caches, and you basically get one new element here and compute over with all the keys, then the dot products, and produce your outputs with the values together. But this is of course very different to having like all the queries also which for the keys which you have during training, and this is. Therefore, like this is becoming a problem. That you just basically have like this memory boundedness there.
Guys, Vikram here.
hey, Vikram.
Nice presentation. Yeah. So a couple of comments I wanted to make. One was on the batch size equal to 1.
Yes.
I think I'm going to argue on this. The reason is batch size equal to 1 is indeed true. If you're going to do it on your consumer grade GPUs or in your local machine where you are trying to answer one query at a time. Whereas if you're in a production deployment, like in the case of Meta, Google, or any of those places who is actually giving you a service, they don't get batch size equal to 1.
Right.
It's much larger than that, right? So in a given fraction of a window of a time, they have thousands of people who are bombarding. So over there, the optimization path is completely different. So batch size of 1 is not practical at that time. The other control knob here is also the latency and the QoS that is needed, quality of service. So if you are fundamentally latency dominated, and if you do not have a window to wait, then hey, reducing your batch size makes logical sense. Otherwise, you will go with larger batch size and go for the throughput, because larger throughput gives you much more other benefit like energy efficiency and all of those that you would try to extract. That is one comment that I wanted to make. The other comment was on your initial set of slides where you spoke about 100 million context lengths and memory capacity being a limiter. The thing here is that slide 6. And here, in the entire presentation, I could not understand something very fundamental. Why do we care about a single GPU memory capacity for going to 100 million tokens? If ring attention is fundamentally driven towards sharing across multiple GPUs, I don't see a single GPU memory limitation being a limiter for the execution of ring attention at all. So they are going orthogonal in size.
Yeah,
so
this was like the motivation for why we need this distributed training. Like this is like one form of distributed training. I've also because today omitted like the different parallelizing forms that we have, like only like covered our ring attention and sequence parallelism. But this was by the motivation, because we at some point can't just handle these things on one single GPU. We need to scale out into distributed settings. Yeah.
Okay, that makes sense then. Okay, so I misunderstood it. And answering one more question from on the chat on Jam. It's a great question on why LLM inferences are becoming memory bound. I think it requires to understand, taking a step back on understanding how a LLM inference actually happens. Fundamentally, an LLM inference can be split into 2 particular stages. Stage 1 is where you have your system prompts and user query, where you perform your computation to perform your self-attention and mass self-attention and whatnot. And in this case, you are primarily generating your first token and understanding your what your prompts are really. In this scenario, you can do batch matrix multiplication, and it's completely compute dominated. When batch size equal to 1, where you are trying to generate one token, after your first token is generated, you need to generate your second token. The second token fundamentally depends on your first token output. So you need to look into what your previous data was. In this scenario, you're fundamentally doing one computation at a time, one token at a time. And one token at a time, you actually have to do QKV, and the value becomes a vector. And that's where your memory bandwidth comes into picture. So this is where your optimization has to change. whether you want to have a trade-off with respect to compute or bandwidth. And this trade-off fundamentally matters when your batch size is equal to 1.
Yeah, thanks, Vikram. I fully agree, and thanks also for clarifying about inference, that we have these 2 stages between the prompt processing and the token by token phase, which is like very different. Also, in reality, of course, the memory for the keys and values, the key and value caches, they are a very like a challenge to have, especially if you want to have, like, for example, pipeline parallelism and other forms of parallelism, where they need to store them even for sequences which we currently don't process at this moment on the GPU, but because it's like next stages on another GPU processing. Yeah, one comment regarding what you said on production and cloud inference. I think this is also like it has to be distinguished between on-premises deployments and cloud deployments, because like there's also like a lot of people for privacy concerns or whatever, they want their company things then in on-premise deployment, and then of course like the economics are not as good as they are for the cloud people, which have, especially for the most popular services like OpenAI and so, they probably have all this exactly what you described, that they have this maximum batch sizes, or they can basically decide on the latency requirements, how much they want to batch together. They always this is like unfortunately not the case for smaller like local deployments, which you have for your own inference, or in a smaller company, where of course like many times you only have then really batch size 1 or like small batch sizes, and this is unfortunately also making like the GPUs and of course also the professional GPUs with like A100s and H100s and so on, like quite expensive for on-premise deployments. Yeah. Like a challenge.
Agree to disagree.
Yeah, I mean, it depends. I mean, like some companies just value this over, like they just take the cost and say it's more important for us to have than this cost saving that we have, like this privacy component. It's like there are different requirements for different people. Yeah.
Yeah, but I think we are entering an open debate topic. And the open debate on-prem that you're mentioning is indeed true. Then I would argue one single statement. What's your business case? Business case is very fundamental here, right? So if you're an on-prem deployment, and if only you're submitting one job at a time or scenarios, that means that your effective LLM usage itself is very, very low. Why are you even building LLM if you're not actually finding much value out of it? Technically, if you create an LLM, or if you're going to use an LLM locally, you are investing millions of dollars to create that model, train that model, fine-tune that model, and generate insight based on the respective data that you have. You actually have to get value out of that generated data point. So you need to have multiple applications to use it. If that's not the case, why invest?
Yeah, I guess like currently it's also like FOMO in a couple of cases. It's like people just want to be like us to play around and also see what's possible with the technology. So there are different motivations. Also, I think this, of course, can be on different time windows. So, for example, you can at night like embed documents and new incoming stuff, and like batch process things beside of direct user queries, which can. So I mean, there's very, very wide field of different like ways to employ in LLMs or multimodal models. Yeah, I just want to say that in some situations the what you say, like this batch size 1 case is unfortunately still happening.
I mean, it is happening. I'm not disagreeing. But what I'm trying to argue is that, hey, that is not an optimal way to design your solution. And if you're going with batch size 1, you are fundamentally trying to design a solution that may not actually cater to a large audience. An individual user for a mobile developer kind of a thing, it makes logical sense, but not beyond that.
Yeah, I agree. Okay, should we maybe then close the session for today and Thanks. Why do we need LLMs? Yeah.
Why do we need like look, I mean, like why do I need LLMs? I don't know. I've met like interesting people while working on them, so that's enough motivation for me. In all cases,
I'm
like
still looking forward to Llama 3. I mean,
yeah,
it's like a big event this year,
yeah,
hopefully.
no comment, no comment, but we'll see. No comment. Like
Yeah, okay, great.
but but yeah, honestly, Andreas, like thank you so much. I really enjoyed like sort of the breadth that you covered and all the references. So please share your slides. I really
Yeah.
want to like jump in on all of these papers. I think if you want to pick up any of these papers for a future talk, it's probably going to be like a great
Hmm.
one. Andres has like also been like actively working on a working group on like ring attention where people are trying to produce like and train these results. So if you're interested in learning how these things actually work, make sure to ping him and join the ring attention channel. And yeah, please just drop a bunch of emojis on Andreas. And thank you so much, everyone, and see you next week.
Yeah, next week we will have Triton, I guess, right? So this is also a very interesting topic.
Yeah,
See
like
you.
I think we finally want to understand the programming model. So yeah, we're gonna have Umer be giving us a nice tutorial there.
Yes.